Hello everyone. The title of this video is Graphing Functions Using Stretches and Compressions. Now, every example I'm going to be doing in this video is taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 3.5, called Transformation of Functions, and I'm under the heading Graphing Functions Using Stretches and Compressions. Each example I do will be either an example from the reading or one of the try it problems from the reading or one of the exercises at the very end of the section related to this particular objective. So the first example I wish to do is example 13 from the reading, from the text. So let's take a look. So there's some stuff for you to read, of course. And here's example 13, graphing a vertical stretch. All right, so the first things we're going to talk about is stretching or compressing a graph vertically, right, up and down. So here a function, say p of t, models the population of fruit flies over time, right? And this graph is shown here. And I'll draw a rough sketch of this on my paper as well before I go back. And what we're asked to do, it says here, a scientist is comparing this population to another population, Q, whose growth follows the same pattern but is twice as large. So sketch a graph of this population. All right, this population Q. All right, so first I'll graph the growth rate pattern for population P. All right, so here on my paper, I have a very rough sketch by hand of that growth pattern, that function P for the growth of a population P of fruit flies over time T. So I got P in red here. Right? Now we're asked to graph the function Q, right? Q of T, where the scientist says that this population Q has the same pattern as population P, but twice as large. So it's equal to P of T, but then times 2. Alright, they said it was twice as large. Alright, so let's see what that does. Alright, if I take a function and then multiply the entire thing on the outside by a number like 2. Alright. Well, hopefully, now I'm going to make a table as well. Right, we have t's, and then we know values of P of T. Right, we're given when T is 0, P of T is 1. Then a bunch of points here that I don't know exactly, and then I know 3, 3. I just look for some nice corners. Right? Input 3, output 3, and then a bunch of points in here, and then 6, 2 was another one I saw on the graph. And then finally 7, 0. Alright, so we know that P of 0 is 1, P of 3 is 3, P of 6 is 2, P of 7 is 0. Right. I'm going to add to this table, and we're going to make a list of outputs for Q of T. Right now Q of 0, right, should just be 2 times P of 0. So that'd be 2 times 1 or 2. Right. And really all I'm doing, according to this rule, is just doubling the outputs from P of T, right? So 2 times 3 is 6, 2 times 2 is 4, and then 2 times 0 is 0. And let me plot these points. So you got input 0, output 2. Input 3, output 6, right? So again, the output is doubled. So instead of 3, 3, I'm at 3, 6. For this function Q, we have input 6, output 4. So instead of 6, 2, now I'm at 6, 4. And 7, 0. Right? So still 7, 0. and it follows the same pattern, right? That's what was said to us. So it kind of curls up from this point to this point, then is in a straight line, and then another straight line down. So here's the graph of Q, right? That has the same pattern, not the exact same shape, but the same general pattern, and double the size, right? Double the outputs. And we would call this a vertical stretch, right? Because if you look at this, all the points on the red graph, their distance from the horizontal axis, their distance from the t-axis gets doubled. It gets stretched away, pushed away from the horizontal axis. So this would be a vertical stretch. Right. And what I want to do on a separate page now is just describe vertical stretches in general. All right, so vertical stretches and compressions. All right, so given a function, given function, say f of x, so we're starting off with a function f of x. If you simply multiply f of x by some number bigger than 1, like 2, like we had here, if you leave the rule the way it is and multiply it by some number bigger than 1, you cause a vertical stretch. So the transformed function not function, that's a C, sorry, function, y equals a times f of x. So again, you leave f of x the way it is and just multiply the whole thing on the outside by a number a, right? A is a constant. A is a number. If a is bigger than 1, like 2 or 3 or 1.5, whatever, the graph of f, I'll say the graph of f is vertically stretched by a factor of a. By a factor of a. Now vertically stretched means this. Now here's the x-axis. It just means all the points on the graph are pushed further away from the x-axis. That's what it means to be vertically stretched. And by a factor of a simply means that's how far the distance is multiplied by, right? So like on this graph here, there's a vertical stretch by a factor of 2, they would say. Because every point on the red graph, the distance to the horizontal axis is doubled, is multiplied by 2 to get on the green graph. Right, like this distance here is 3 units and this distance here is 6 units, right? Every distance got doubled, right? This distance is 2 units, and then the distance to the green graph is 4 units, right? Every distance got doubled. 1, then 2, 3, then 6, 2, then 4, and so on. All right, so that's a vertical stretch. Now, if a is between 0 and 1, So if you multiply a function by a half, or 2/3, or 0.256, something between 0 and 1, then they would say the graph of f is vertically compressed. Vertically compressed. Again, by a factor of a. Now, vertical compression means the following. Again, here's the x-axis, the horizontal axis. When I say a graph is vertically compressed, that means all the points on that graph are pushed closer to the x-axis. They're squeezed in, compressed in, instead of stretched out. Right. And we'll get to examples like this in a second. Right. So please know this. Know what it means to stretch and compress a function vertically. Now, if a is negative, then there will also be some sort of reflection across the x-axis involved, but I'm not going to write that. Right. We've seen reflections in a previous video. Okay. All right, so that was example 13 from the reading, my first example. The next one I want to show you, example 2, is example 14 from the reading. All right, so let's go back to the text. And I'm going to scroll down. Again, you got some stuff to read. And here's example 14. And we have a function given to us as a table, right? A table of just 4 ordered pairs. And here a function f is given in this table. And we're asked to create a table for the function g of x equals 1/2 times f of x. So you see f stays the way it is, but then you multiply it by a half, a number less than 1. This is going to cause a vertical compression, as we'll see when I graph this as well. All right. Okay, so I've written out the table they gave us, and they told us, that g of x, this new function, is just a transformed version of f. It's half times f of x. All right, and then using the inputs from our table here, we see that g of 2, just replacing x with 2 here, right? X with 2, the first column, would be half times f of 2, which would be 1/2 times 1, or just a half, right? So I'm going to start making a nice row here for outputs of g, right? So when the input's 2, the output of this g function, this half f, is just 1/2, right, or 0.5. And then g of 4, right, when x is 4, g of 4 would just be half of f of 4. So that'd be 3/2, right, half of 3. And really all I'm doing here is multiplying all the outputs from f, right, taking f of x, and multiplying all the outputs by a half, 7/2 and 11/2. Right. And what we're going to see is that this g of x function, this half of f of x, that's a vertical compression of f by a factor of a half. Right. And we'll see what I mean when I'll make a rough sketch here. Right, so there's x-axis, y-axis. I was supposed to go to 11, 9, 10. Right, sorry about this. That's 11 at the top. And I'll mark off the halves as well. Right, that should be good enough. Alright, so I'm going to graph f in red. So 2, 1, right? Input 2, output 1. There's that point. And notice that that is, 1 unit away from the horizontal axis. Right? Then 4, 3. Right? 4, 3 is on the graph of f. 6, 7 right, 6, 7 on the graph of f, and 8, 11. Right, sorry, all the way at the top here. Right. So the red graph, all these red dots I'm making are f, the function f. All right, and then I'm going to plot in green. And again, if you can't see red or green, I apologize if they're different. Hopefully you can tell the difference between them. Between the, maybe not see red or green, but see other colors. Input 2, output a half, right? So a half is like here, right? Input 4, output 3 halves, or 1 1/2. So like here. Input 6, output 7 halves, which would be 3 1/2, so about here. And input 8, output 11 halves, which would be 5 1/2, it's about here. Right, okay. And there's the graph of G, right? So notice they don't form the exact, it's not the same shape, right? Runs roughly in the same pattern, the same, but it's not the exact same shape. But G here is the graph of f vertically compressed. Right? Vertically compressed by a factor of 1/2, right? It was times 1/2. Right, and what that means is that all the distance, if you look at f, right, all the points of f get pushed closer to the horizontal axis, right? They all get pushed closer to the x-axis. So you see this distance was 1 unit, and then it got cut to a half, right? This distance was 3 units, and then I got cut to 3 halves, right? Half the distance. This distance is, 7 units, which got cut to 7 halves, right? And then finally this distance here was 11 units, which got cut to 11 halves, right? Every distance, all the points on the graph of f, their distance to the x-axis got cut in half, right? They were pushed closer to the x-axis. That's vertical compression. If they're pushed further away from the x-axis, that's vertical stretching. And hopefully after a while here, after several examples, you'll understand the difference. Okay. All right. The next example I wish to show you is the try it problem number 9 from the text. So let's take a look at that, which is the very next one. All right. So another table here. Again, a function f is given as a table. There's only 4 ordered pairs again. And we're asked to create a table for the function g, where g of x is just f of x times 3/4. So again, it's the original function, but just multiplied by a number. This will cause a vertical stretch or vertical compression. And notice that number is less than 1, right? 3/4. So we're going to cause a vertical compression by a factor of 3/4. Right, so again, I'm not going to draw these this time. I'll just write the table. Right, so we're looking down here, and they told us, g of x is 3/4 times f of x. All right, so I'll make a little row here for g. What are the outputs of g when x is 2, 4, 6, and 8? So again, g of 2 would just simply be 3, just replacing x with 2 in this rule, would just be 3/4 times f of 2. But that'd be 3/4 times 12, which is 9. All right, so on the function g, you'd have the point 2, 9, right, which is 3/4 of 12, right? And that's a vertical compression by a factor of 3/4. Right. G of 4, right, would just be 3/4 times f of 4. So 3/4 times 16 would be 12, right? So 4/12 would be on the graph of g instead of 4/16. And then so on, right? And then 3/4. Basically, I'm just multiplying these outputs from f by 3/4. 3/4 times 20 is 15. So you have 6/15, 6/15 on the graph of g. And 3/4 of 0 is 0, so you'd still have the point 8, 0. Right? Any point that's on the x-axis that can't be pushed any closer to the x-axis, right? It's already on it. All right, so here's the table they wanted, the outputs for G with those inputs of 2, 4, 6, and 8. And again, we could say that G is the graph of F vertically compressed, because it's a number less than 1 that we're multiplying by, or between 0 and 1, vertically compressed by a factor of 3/4. And again, if you want to plot the points in C like I did in example 2, you'd see that the points on F get moved closer, they get pinched closer, compressed closer to the x-axis, right? And by a factor of 3/4, right? Like the point 212, that's 12 units away from the x-axis, and then the point 29, that's 9 units away. 9 is 3/4 of 12, right? The distances get compressed by 3/4, a factor of 3/4. Hopefully that makes sense. All right. Next example. All right, now I believe I'm going to get into some horizontal stuff. All right, let's see. I got example 17 from the text I want to show you. So it's 15, and now we're getting into horizontal stretches and compressions. And you got some reading to do here. Example 16. I want to show you example 17, another one where a function is given to us in a table format, right, with just 4 ordered pairs. And notice, instead of, we're given a function f of x, and we're asked to consider the function g of x equals f of, and it's not just x, it's not just f of x, it's f of half x. So the x's are replaced by half x in the rule for whatever the rule for this function looks like. So here the multiplier of a half is not on the outside, it's on the inside of the function. And if you recall from horizontal shifts and stuff, when something's done to the inside of the function, right, it causes horizontal transformations. When something's done to the outside of the function, it causes vertical transformations. All right, so I'll write this out, and we'll talk about, how would we figure out inputs and outputs for this function g. All right, so here was the table given. All right, maybe I'll start plotting some points too. All right, let's do that. So here's 2, 4, 6, 8. And we have outputs up to 11. There's 11, 1, 3, 7. Okay. So I'll plot f in red. Right? You have input 2, output 1, input 4, output 3, input 6, output 7, input 8, output 11. Right? We had this graph up earlier. Right? There's f. Now the function we're given, or we're asked to write a table for, is g of x equals f of half x. Right, where the half multiplier is inside, right? X is replaced by half x in the input area. Right? Now, watch what happens. If I try to keep, if I make a little row for g of x here, I'm going to make a row for g of x. And I say, okay, let's use these same inputs. And I say, what's g of 2? So I replace x with 2. Well, according to this rule, that would be f of, half times 2. That'd be f of 1. So g of 2 would be f of 1. And there are no inputs of 1 up here. I do not know f of 1. All right. This is unknown. I do not have this in the table. So you see, I need to change the inputs. I can't use 2, 4, 6, and 8 for x here. Because, that's going to give me, now I can use 2, I guess, but yeah, I can't, I mean, I can use 4. That'll give me f of 2, which I know, but, I don't know when I plug in 2 for x, I don't know f of 1, right? If I plugged in 6 for x, that would give me f of 3, right? Because it's half of 6. And again, I don't know this, right? What's f of 3? I only know f of 2, f of 4, f of 6, and f of 8. I don't know f of 3. Same thing for, well, I guess g of 8 would work out. But these two are no good. But g of 4 and g of 8 I can find, right? G of 4 would be f of 2, and f of 2 is 1, right? So g of 4 is 1. So I know I can plot the point 4, 1. 4, 1. And you see how that, the graph of f in red, see how this graph I'm making now for g is to the right. It's a horizontal change, not a vertical change. G of 6 I said was unknown. G of 8, right? G of 8 would be f of 4, which is 3. So 8, 3, right? So 8, 3 would be on the graph of g right here. And again, you see how this point here at 4, 3 get bumped away from the y-axis. It's getting pushed horizontally. All right, so now I can, if I want to use, I found I had f of 2, f of 4. I'd have to plug in 10. I'm sorry, not 10. I'd have to plug in 12, wouldn't I? I'd have to put in 12 for x to get f of 6. Right, half of 12 is 6, and then f of 6 is 7. So g of 12 would be 7. Right, so I have to add to my little graph here. Here's 12. Right, g of 12 would be 7. Again, that point pushed away from the y-axis, right, a horizontal push. And then to get 8, I'd have to put in 16 for x. G of 16 would be f of 8. And f of 8 was 11. Right, so g of 16 would be 11. Right, so 16 for the input. G of 16 would be 11. There's function g, those 4 points here. And notice how they're the points of f just pushed away from the y-axis. They're pushed horizontally. And what happened is the distance from the y-axis got doubled here, didn't it? All right, if I look at the distances from the y-axis, this point here was 8 units away, and then the point on G was 16 units away, right? Doubled. This point here, right, was 6 units away. The point on G was 12 units away from the y-axis. So the distance from the y-axis got doubled. This point here was 4 units away from the y-axis, and the point on G is 8 units away. Doubled. And then here, this is 1 unit, and then the point on G is 2 units, and then the point on G is 4 units away. Doubled. Right. But for every single one of these points on F, right, the point on G is twice as far away from the y-axis. Right. And that's going to happen in general. So if you take a function, f of x, if you replace x with a number times x, that's going to cause a push either away from the y-axis or toward the y-axis, a horizontal stretch or a compression. But this would be a horizontal stretch in this graph here. They would call this a horizontal stretch because the points are getting pushed, from F to G are going away from the y-axis. And it's by a factor of 2. Right? by a factor of 2 because the distances got doubled, right? 8 to 16, 6 to 12, 4 to 8, 2 to 4. So yeah, there's a half here, all right, which is going to be a bit confusing. You might think, oh, it's a horizontal compression by a half. No, it's a stretch by 2 by the reciprocal. All right, it's by the reciprocal, and you got to be careful with that. All right, so in general, all right, let's talk here on this page about horizontal stretches and compressions. So again, we're given some function, f of x, and then we transform it. The transform function y equals, f of, and you replace x with, and I'll use the same letter they use in the text, b times x. So in my previous example, the b was a half. Right? So if I replace x with b times x, then the following stuff will happen, right? If b is greater than 1, right, so not like my last example. We'll see an example of this coming up. In the last example, it was less than 1, right, half x. But if b is greater than 1, you're not going to cause a horizontal stretch. You'll cause a horizontal compression, right? The points will get closer to the y-axis. Right, so the graph of f will be, or is, horizontally compressed. Horizontally compressed by a factor of not b, but 1 over b, right? The reciprocal. Right, this is the reciprocal of that multiplier, right? Just like in my first example, when I replaced x with half x, we got horizontally changed or stretched by a factor of 2, right? The reciprocal of a half. Right. Okay. And then again, what do I mean by horizontally compressed? Well, that means, here's, say this is the y-axis, the vertical axis. Horizontally compressed means that all the points are moved closer to the y-axis, right? In the earlier example, the previous example, they were moved farther away. So that's a horizontal stretch, and that's what I'll talk about now. Right? So the second case is, if b is between 0 and 1, right? Like in my example, right? It was half x, right? B was a half. Then the graph of f will be horizontally stretched, as we saw. Is horizontally stretched. And once again, by a factor of not b, but 1 over b. Right? Again, the reciprocal of b, like we saw in example 4, or example 17 from the reading. And then what do I mean by horizontally stretched? Right, again, here's the y-axis. Right, when I say a function is horizontally stretched, that means the points on that function are pushed away from the y-axis. Right, like in the graph here, right? The graph of f, those points got pushed away from the y-axis by a factor of 2, right? Double the distance. All right, so again, keep this in mind, right? This is going to be how all horizontal stretches and compressions go. And then also something they have in the book that I'm not going to write here. If b is negative, then there will also be involved a reflection across the y-axis. Right, but I've already done a video on reflections, so I'm not going to talk about that here. Right. Okay. So, next example. All right, try it number 11 from the text. Let's take a look at that. So example 18, try it 11. All right, so here they're asking us to write a formula for the toolkit square root function horizontally stretched by a factor of 3. All right, so remember the toolkit the square root function is this. F of x equals, the square root of x. That's the basic square root function. And they're asking us to horizontally stretch this by a factor of 3. Now to do that, it's very simple. You're going to replace the x's, right? Because that's what happens in these, right? X is replaced by bx, where b is the reciprocal of the factor it gets stretched or compressed by. All right. So we're going to replace all the x's in the equation, all the x's in the rule, with not 3x, but the reciprocal, 1/3 x. Right? If I want it to stretch by a factor of 3, we have to replace x by the reciprocal of that 1/3 times x. Again, reciprocal. So the rule we're looking for is y equals f of 1/3 x, right, instead of f of x, which is the square root of 1/3 x. Right. So y equals the square root of 1/3 x. And let's see that actually working out. All right, and I'm just going to show you on the Desmos site. So I go to that free online graphing calculator at Desmos, right, desmos.com. And the first function we're given, right, is the square root function. Y equals the square root of x, which you should know what that looks like. All right, and I'll put a table up for this so we can see some points that are plotted, and I'll change some values in the table. Let's go 0 here, 1 here, 4, 9, 16. All right, so there's a table, and now a bunch of points are plotted. All right, you see 0, 0, you see 1, 1, you see 4, 2, 9, 3, 16, 4, right? And I'll even put the y-axis up so we know where the y-axis is. That's x equals 0, right? Vertical line. So that solid black line there, maybe I should make it dashed. I'll make it a dashed line because it doesn't actually belong to the graph here, right? Okay. So if you look at this, right, there's our square root function. And this point is 0 units away from the y-axis. This point is 1 unit away from the y-axis. This point is 4 units away from the y-axis. This point is 9 units away. And we were asked to stretch this horizontally by a factor of 3. So 1, 1 would move to 3, 1, right? 4, 2 will move to 12, 2. 9, 3 will move to 27, 3, okay? Every point, the x-coordinate gets tripled. That's what they mean by horizontally stretched by a factor of 3. And I showed you how to do that, right? We go y equals, and instead of the square root of x, I replaced x with, the reciprocal of 3, 1/3 times x. And look at that. Look at that red graph. That's definitely the points on the blue graph pushed away from the y-axis. And let me make another little table here. All right, let's duplicate that. All right, so you'd have 0, 0, 3, 1, then 12, 2. All right, a third of 12 is 4, and a third of 27 is 9. Right, so 27, 3. A third of 48 is 16. Right, and look at these. Look at these points. All right. So definitely again, the dotted line here is the y-axis. So here's 1, 1. Well, first of all, 0, 0 is on both of them. If you multiply 0 by 3, it's still 0. So the distance is still 0 for that point. But then every other point, right, gets pushed by a factor of 3 away from the y-axis, right? The distance from the y-axis is tripled when I replace x with 1/3 x. So you see 1, 1 on the blue graph, 3, 1 on the red graph. That's 1 unit away and 3 units away from the y-axis. Here's 4, 2 on the blue graph. There's 12, 2 on the red graph. 4 units away and then 12 units away. Triple the distance, a stretch by a factor of 3 horizontally. Here's 9, 3, 27, 3. 9 units away from the y-axis on the blue, 27 units away from the y-axis on the red. 3 times the distance, stretched by a factor of 3. All right. So, but it's just as simple as replacing x with b times x, where b is the reciprocal of the factor you want to stretch or compress by. Right. It's really that easy if you get the hang of it. All right. All right, so moving on. All right, so for the next few exercises, and I think the rest of them, we're just asked to describe the transformation that occurs. So describe how the graph of each function is a transformation of the graph of the original function. So the original function's y equals f of x. And number 6, you have g of x equals 6 times f of x. Notice it's a number on the outside multiplied by f of x. So this is going to cause some sort of vertical stretch or compression. And this should vertically stretch. That's a number bigger than 1. This should vertically stretch f by a factor of 6. All right, the vertical stuff is nice. Right? It's just 6, and that's the factor it'll stretch by. And that's all they want. They just asked us to describe what would happen. All right, and I could go and back to Desmos and show you any function and see that this happens. Right. So if I go back here, let's clear this stuff that we have right now. And I'll take another one of those toolkit functions. How about y equals, the square function, x squared. Or sorry, f of x. Let's do f of x equals x squared, right? And then just do y equals, 6 times f of x. And look what happened, right? So the original function is the purple one, and the red one's the new function, 6 times f of x, 6x squared. And you see you got the point 1, 1. And maybe I should make some tables here. Maybe I shouldn't have duplicated them. How about that and that? Alright, then put a table up. Okay, and look, right? You can even see in the tables. On the original function, you got negative 2, 4. On this new function, you have negative 2, 24. That's 6 times the distance from the x-axis. 6 times the distance from the y-axis. 6 times the distance from the x-axis. 6 times the distance from the y-axis. 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 6 times the distance from the y-axis So you got this 0, 0, sure, right? That's on both of them. You know, this has 1, 1, 1, 6, right? 6 times the distance from the y-axis. And again, this has 2, 4. This one has 2, 24, 6 times the distance. All right, we are the red graph is the purple graph vertically stretched by a factor of 6. And it's just simply, you know, multiplying the original function by 6. All right. Okay, example 7. All right, so here we have g of x equals, and you know, we start off with f of x, and you know, notice this 2 here is not on the outside, it's on the inside. This is f of 2 times x. So if x is replaced with 2 times x, remember that causes the x coordinates to change by a factor of a half. And that's less than 1, right? This number is bigger than 1. The reciprocal would be less than 1, so you'd have a horizontal compression. Right? This is going to cause a horizontal compression, or this will horizontally compress f by a factor of a half. All right, and again, that's all they wanted, but I'll show you an example. All right, I'll show you an example. Let's go back, back here. Put in one of those toolkit functions. Say f of x equals, I'll just do the square root of x again, and y equals f of 2x. And you see how the blue graph is closer to the y-axis than the red graph. There's a horizontal compression, and it's a compression by a half. All right, let me put some tables up, and you can see. All right, well, not with the negative numbers, but even with where they're actually defined, you see 0, 0, 0, 0, 1, 1. And then this would have 1/2 1. All right, let me show you. Put in 1/2. See, 1/2 1. So 1, 1 on the red graph, the original, and then when I replaced x with 2x, it got moved to a 1/2 1. Right, the horizontal compression by a half is now half the distance from the y-axis. All right, this has 2 square root of 2. This should have 1 square root of 2. All right, so there's 2 square root of 2, and then 1 square root of 2. You know, on the red graph, it's 2 units away from the y-axis. On the blue graph, it's only 1 unit away. It's half the distance. All the horizontal distances, all the distances from the y-axis got cut in half when I replaced x with 2x. Okay. All right, let's go back. And next example, we're doing the same thing. So here we have g of x equals f of 1/5 x. So again, notice the 1/5 is on the inside, not the outside. So this is going to cause a horizontal transformation. Now, is it going to be a stretch or compression? Well, remember, it gets all the x coordinates will get multiplied by the reciprocal of this number, by 5, and that, you know, because this is less than 1, you know, the reciprocal will be bigger than 1. This is a horizontal stretch, right? So this horizontally stretches f by a factor of the reciprocal of 1/5, right? By a factor of 5. And that's all they wanted, right? Just describe what happens to the function f. And I'll show you an example. All right, I'll show you an example with one of the toolkit functions. Let's pick one we haven't done in a while. How about reciprocal function? F of x equals 1 over x. All right. So there's this blue graph. All right. And then when I plug in replace x with 1/5 x. So y equals f of, and then instead of x, I go 1/5 x. Look at that green graph. See how the points on the green graph are farther away from the y-axis than the blue graph. And in fact, they're 5 times farther away, right? Here's 1, 1, and then here's 5, 1. Right? The points on the green graph are 5 times farther away from the y-axis than the points on the blue graph. And that's when I replace x with 1/5 x. Yeah. Nice. All right, and then the final example I have here actually combines a couple. So example 9. This actually combines a couple transformations. I know I didn't talk about, I didn't say it. I said it out loud, I didn't write it. But we have seen in a previous video of mine reflections. So this is actually going to cause two things to happen. We have g of x equals -1 times f of 3x. So this -1 on the outside, remember multiplying a function by -1 will reflect it across the x-axis. That causes a vertical reflection. So we have a reflection across the x-axis. Then, and you see this now, x is replaced by 3x, and the 3 is on the inside, so it's going to cause a horizontal shift or compression, horizontal stretch of compression. Then we horizontally, and this will be compression, right? Remember, if there's a 3x here, I replace x with 3x, that's going to multiply all the x coordinates of the original graph by 1/3, right? If this number times x is bigger than 1, the reciprocal is less than 1, causing a compression. Then horizontally compress by a factor of 1/3. Right, and so this is what would happen. It's a couple transformations at once, and that'll be the whole next video too. In the next video, it's going to be about combining transformations, horizontal transformations, vertical transformations, shifts, stretches, compressions, reflections, all that stuff. All right, this just combines a couple of them. All right, and once again, I'll just show you a quick example of one of these, all right, of this happening. So I'll pick one of those toolkit functions. So how about the absolute value of x? Why not, right? It looks like this. Y equals f of x equals the absolute value of x, right? One of those V-shaped graphs got 1, 1, 2, 2, 0, 0, -1, 1, -2, 2, and so on. And look at what happens, right? Y equals -f of 3x. So do you see the reflection? Right? It definitely reflected this across, right? In fact, let me put up just -f of x. Y equals -f of x. All right, so that red graph that just popped up, this graph, let me turn this one off, right? Y equals -f of x is just a reflection across the y-axis, and then you replace x with 3x, causing a horizontal compression by 1/3, right? You see the points on the black graph are closer to the y-axis than the points on the red graph. And in fact, they're closer by a factor of 1/3, right? Here's the point 3, -3, and then here's 1, -3 on this graph, right? Which is, 1/3 of the distance, right? 1 unit versus 3 units. Okay? And, here's the point 6, -6 on this graph. Multiply the x coordinate by 1/3, you got 2, -6 on this graph, right? But yeah, so there was a reflection across the x-axis, and then a compression by a factor of 1/3 horizontally, right, to get that final graph there. Okay, and that was how I described it on paper as well. Right? Reflection across the x-axis, then horizontally compressed by a factor of 1/3, and you'll get your final graph no matter what f of x started off being. All right, so that's a lot of stuff there. Again, the key takeaways are the following. To cause a vertical stretch or compression, you just simply take your function and multiply it by a number. If that number is greater than 1, it's vertically stretched by that factor. All right, you just multiply all the y coordinates, all the outputs, by a. And if it's less than 1, but still positive, right, like a half or something, you have vertical compression. Right? Again, just multiply all the y coordinates by a. Then for horizontal stretches and compressions, one more time, you take f of x, replace the x's with bx. And if you do this, if you replace all the x's with bx, you're going to be multiplying each x coordinate by 1 over b. Right? So if b is bigger than 1, 1 over b will be less than 1, you'll get this horizontal compression by a factor of 1 over b. And if b is less than 1 already, 1 over b is going to be greater than 1, so you'll get a horizontal stretch. Right? Points will be farther away from the y-axis by a factor of 1 over b. Right. So those are the key takeaways, and I'm hoping that watching me go through these 9 examples here help you in some way when you're asked to perform vertical stretches or compressions or horizontal stretches or compressions on your own. And thank you very much for watching.